Now, in previous sections, we've been talking about optimization problems. These are either maximization or minimization. And these involve a planner who has resources, who either wants to maximize profit or minimize cost, or maximize some other quantity or minimize some other bad effect. But in this case, you have basically one agent, one person making a decision based on a situation, and they're trying to get the best possible result from the situation that they have. Now, in game theory, you don't have one person, you have two or more people, each of whom controls some of the variables, but not all of them. And usually, one person's gain is the other person's loss. We will talk about zero-sum games in which that is actually true, that the gain of one player is exactly equal to the loss of the other player. So the two have interests that are directly conflicting. So again, this is what's called a zero-sum game. A game that's not this way is non-zero-sum. So non-zero-sum, there may be some additional opportunities for cooperation and you get a win-win. But in a zero-sum game, any additional gain achieved by one player is going to be a loss to the other player. So you see this sentence here, usually the players will not agree as to which event should occur. Now, if my gain is your loss, certainly we're not going to agree on what event should occur. So when you do have a two-player game, you can set this up as a matrix, as we'll see. And game theory is the method, standard method for finding what the strategies of the two players should be. So we're doing two-person, zero-sum games. Now, the solution is based on the principle that each player tries to choose his course of action so that regardless of what his opponent does, he can assure himself of a certain minimum amount. Another way of saying this is that the best strategy of a player is going to be a strategy where even if the other player knows what the strategy is, he can't get any additional benefit through that knowledge. So the best strategy assumes that the other player is smart and can reason as you reason. He can put himself into your head. And you also can put yourself into his head. So again, you want to have a strategy where even if the other player knows what strategy you're going to use, he can't take advantage of that. So here we say most recreational games such as tic-tac-toe, checkers, backgammon, chess, poker, bridge, etc. can be viewed as games of strategy. There are also gambling games where there's some probability that's involved. Now you can use game theory for both of these types of games. So let's talk about some simple games. Maybe these seem too simple, but the same principles are involved in these very simple games as in more complicated games. Let's start out with this example. Two stores R and C are planning to locate in one of the two towns. Now, I should just say that in a lot of economics can be considered as a game because you have competitors who are making choices and they're trying to maximize their profit. And their profit gained is profit that you lose. So it's really a zero-sum game. So you have two stores that are planning to locate in one of two towns. In figure 49, town 1 has 60% of the population, that's here. Town 2 has 40%, that's here. If both stores locate in the same town, they'll split the total business. But if they locate in different towns, each will get the business of that town. So where should each store locate? So we put store R's strategies here and store C's strategies here. R is for row, C is for column. So store R locates in town 1. Think of what happens for the two options for store C. If store R locates in town 1, then if store C also locates in town 1, they're in the same town, so they split business 50-50. If store R is town 1 and store C locates in town 2, then store R gets the business of town 1 because store R is closer to the people in town 1. And store C gets the business in town 2, which is only 40%. So we can put store R's percent here. So we can say that store R gains 60%. That's the same thing as saying that store C loses 60%. So store C gets 100 minus 60, which is 40. Right? So similarly, if store R locates in town 2, if store R locates in town 2, if store C locates in town 1, then store C is closer to the people in town 1, and store C gets the business of town 1. So store R would only gain 40% of the business, so that's why we have a 40 here. And if both stores locate in town 2, they both get 50% of the business. Right, so this is what we call a payoff matrix. Looking at this, this is the payoff from store R's perspective. And it's the negative payoffs from store C's perspective. Store R here gains 50% of the business. Store C loses 50% of the business. All right. So how should the two players play in this case? Well, you look at this 60. This 60 looks like a plum, right? Both players are going to want the 60. So you might say store R should locate in town 1, and then he can get 60%. But store C isn't that stupid. Store C realizes that if store R chooses town 1 and store C chooses town 2, he's going to lose 60%. Well, that's just not a smart option. In fact, store C always does better choosing town 1 than town 2. And store R always does better choosing town 1 than town 2. Think about it. If store R chooses town 2, then store C has two options. If store C chose town 1, then store R only got 40% of the business, which is worse than the 50% he would have gotten if he chose town 1. On the other hand, if store C located in town 2, if store R had done town 2, he'd get 50%, which is worse than the 60%. So you can see that in every case, store R choosing town 1, he's going to be better off no matter what store C chooses. And in fact, the same thing is true for store C. Store C is better off choosing town 1 no matter what store R chooses. So they're both going to end up choosing town 1, and they're both going to end up getting 50%. All right, so here's a case where there's no controversy. Although the interests are opposite each other, they're both going to agree to choose town 1. They're both going to get 50% of the business. Now, what we have here is a general setup that we can apply to more general games. Here we listed the strategies of store R and the strategies of store C. And in each box in the table, we put the result of that combination of strategies. Now, we could have 1, 2, 3, 4, 5, 200 strategies for store R and umpteen many strategies for store C and do the very same thing. And we get what's called a payoff matrix, where the ij entry of the payoff matrix tells what happens if store R does strategy I and store C does strategy J. Right, so that's this definition down here. Let G be a M by N matrix. M is the number of strategies of the row player, N is the number of strategies of the column player. The entries of this matrix are Gij. So it's a M by N matrix, as it says here. G can be interpreted as the payoff matrix of the following matrix game. Player R chooses any row I, and simultaneously player C chooses any column J. The outcome of the game is that C pays to R an amount equal to Gij. Right, so again here, player C's loss is player R's gain. So if Gij is less than 0, then R pays C. So we'll go on and do some more examples in the next video.